I'm from another industry focus, then landing by Schneider in Switzerland, the first company who did the catheters with Dr. Krumsiek. And until today, we developed more than 150 catheters, about 25 stents, and a lot of different more products. The first, let us come back to the history. September 16, 1977, Zurich, Switzerland. There, Dr. Andreas Krumsiek did the first step for the history of the interventional cardiology, what we call today PTCA. His first intervention was in a gentleman, Adolf Bachmann, 38 years old. I met the person many times, and he has a very nice life. Andreas was a radiologist and inventor, because he invented this balloon catheter, and was his invention and his product until he died in year 85 in Atlanta, USA. After this came a hole in the wall about interventional cardiology. Schneider company, who did the catheters for Krumsiek, was very close to stop everything because everything worked over Krumsiek until he died. Then few European doctors come to the idea to jump to Schneider and let all the catheters and began to work alone. Swiss, German, and some American doctors. The difference was by Krumsiek, Schneider built about 200 catheters per month. For the rest of doctors, built about 20. That was a start. Then came Pfizer to buy Schneider, and then became the start of new developments, like you can see here. The balloon materials was a problem. The Krumsiek catheters was built in material PVC, low pressure, the balloon and the catheter body, and the people began to ask for higher pressure balloons. Then is my beginning. We start to check for materials. We tested the completely nylon family and the polyimide 12 family for 248 different materials. I had a team for 6 people, 12 months, and did just balloons. We built around 20,000 balloons to testing to find the best one. Because in this time, the doctors began to talk about the restenosis. And we found out, with the help of these doctors, that there was no restenosis, was no stenosis, because was at the end of the balloon. So on both ends of the balloon, proximal and distal. So we tried to find a softer material, high resistance, what we can go to high pressure. The first high pressure balloon we did was in 1994 and was made for a post-dilatation, as we know today, the non-compliance balloon. And that was the first time we had a balloon in the market, and you can press until 25 bars. That was very interesting because at the time, and many of you knows, the stent was built and crimped in the operation room from the doctor himself, put in the balloon, crimping by hand, and both ends sometimes was not completely implanted. And we start then to make a very short balloon, 10 millimeters long, with high pressure to finish the implantation of the stents. The stent was very different from today. The surface was bad. The endpoints from the stent was also not the best, but it was new. And then we have found the control compliance. So we had to control the compliance of balloon because we had at the time know the best picture to know the best measurement systems. You know how complicated are the measurement system for the balloon catheters. We have millimeters, we have inch, we have centimeters. I don't know, it never was installed a correct measurement system, but the interest was more to have this high pressure balloon. Then from German came the idea to eliminate people in the operation room. So The people in the operation room was too expensive, and the Professor Bonzel from Germany came to Schneider and asked us to change the over-the-wire system for a rapid exchange system as we have today. It was done. Then to introduce to the market, we need about 8 years to have a complete market for rapid exchange. The last country was Japan, because they don't want to eliminate the operators in the operation room. So with rapid exchange technology, you don't need the second operator. You have a better wire control, quick catheter exchange, a shorter guide wire, increase the procedure, and less radiation time. That's also very important what we have today. Even today, many companies have over-the-wire catheters because some doctors like to have this with the feeling they have better pushability or not. By the Grunsick time, until 92, the balloon catheter, the balloon and the shaft was gluing, so very difficult to assemble and very poor quality. And so a long space to glue, leading to a long, hard pieces of the catheter and lose flexibility. So then the idea from many doctors, who we flow very well, was to find out why we have this dog boning and to create what creates the distal stenosis or stenosis. We found out the catheter has a long shoulder, along with the 20 degrees. We found out we can make with 42 degrees as we have today, the Celeste design, we avoid the dog boning and the intima inflammation. As I say, the process of the gluing, the step with gluing was 3 to 4 millimeters long. You can imagine if you have a 10 millimeters balloon and you have from both sides 3 millimeters hard place, the flexibility will be very poor. Then we invent the laser welding. That today I think every company do these operations with laser welding. You will see here a part of the welding. So we can have a welding point from 1.5 millimeters length. You increase the flexibility and maneuverability of the catheter. Then we found out also with opinion leaders, when all the most catheters, when you put pressure on the balloon, after 6-8 bars, the inner tubing collapses over the wire. So then the catheter and the wire, during the inflation, move together in the artery, and the tip of the wire can make small damages in the intima. In our case, we invented the innovative design features, material allow high pressure without increase the profile and dog boning. We have flexibility, and our wire is free under the balloon until 18 bars. Then that is the last invention we have here. We create a wall thickness with 8,000 millimeters, so we have an excellent wrap. We have better delivery. We have less trauma possibilities, better navigation, properties of design, and superior balloon material. So that's what we have here. This is one of the last design we did. This one company in India you have here. It's very interesting because we avoid a lot of things. With so thin balloon wall, we can have more pressure. We have better flexibility. We now create stress in the intima. We eliminate dog boning. So a couple of things that was found out during about 20 years develop and 20 years search for materials, design, and balloon form. And also create a form to manufacture the balloons. That's maybe our main point. We have a long history in manufacturing balloons to eliminate all these things that I said before. At the time, we had different applications. So one doctor planning to have the balloon inflated for 20 seconds. The other one liked to have a long time, 1 minute. And the question was, we need to have a fast deflation because inflate is okay. But if you want to deflate the balloon fast. Don't create any problem inside. You have to have a fast deflation time as we have here. I believe today in the market, our balloons are maybe the fastest on deflation. So every doctor can make use. You can wait 1 minute, you can wait 20 seconds, and then deflate fast. That's very important for us. You see here the artery. The artery is tapered even after the dilatation, and we work with it, with this Arbor Glide. We can make this form what you see there. That's my presentation. Thank you. Was very happy to be here. Thank you very much.
Thank you very much for taking us through the history of interventional cardiology from 1977 till recently and giving some insights into the development of the technology. I think we will take the questions at the end of the session. Thank you very much.